All right, so let's see if we can continue this journey of taking off, sort of going down the runway of known values and all of a sudden take off into the unknown value, the general value. So here's a table. Again, the position is given by these numbers here in yellow, 1, 2, 3, 4, 5. This is the where we are in our sequence. And then here's the value of each term. So the first term is 8, the second term is 16, the next term is 24, the next term is 32, the next term is 40. And the question is, can we figure out a pattern here? Well, let's take a look. First I see 8, then I see, 8 plus 8. So I see 2 times 8, and this is actually 3 times 8. This is 4 times 8. Now wait a minute, check out the position. Look at it. If I take 1 times 8, I get 8. If I take 2 times 8, I get 16. If I take 3 times 8, I get 24. This is so cool. It's like a magic thing, isn't it? If I take 4 times 8, I get 32. This is working. If I take 5 times 8, I get 40. So what's the pattern? It's the position multiplied by 8. Position multiplied by 8. Position multiplied by 8. So if the position is n, what do I do? To get the value, I multiply by 8. Or in this case, I'd write it as 8 times n. And so I'd see 8n. So there's the general expression that captures this pattern. If n, for example, were 10, then I know that the 10th term would be 8 times 10, which is 80, which is correct. So you can see that this sort of generalizes the whole thing. All you got to do is look at that, and you get everything for free. If n is 1, then I get 8. If n is 2, then I get 8 times 2, which is 16, and so forth. Very, very cool. All right, how about this one? Let me see if I can stump us at all. The positions given by 1, 2, 3, 4, 5, and so forth. Here are the value of the terms, though. This is a little bit trickier. I see a 5, then an 8, then an 11, then a 14, then a 17. Now, what's going on here? Well, I don't know. Do you see anything good going on here? How does the 5 relate to a 1 that corresponds to how the 8 is relating to the 2? Well, it's not so clear anymore, is it? So let's see. How do I get from 5 to 8? I would add 3. How do I get from the 8 to the 11? I would add 3. Oh, this is good. How do I get from the 11 to the 14? I add 3. So it looks like I keep adding 3 to the previous term. So how do I capture that? Well, what I'm going to do is I'm going to take a look at this. Now, what if I just took 3 and I just multiply that by the position? That would give me 3 times 1. Well, that's just 3. To get to 5, I'd have to add 2. But what if I tried that here? What if I took the 2, multiplied it by that 3, that gives me a 6. How do I get to 8? I add 2. No, wait, this can't be happening. Oh, let's see, this can't be happening. What if I took this 3, multiplied it by our 3, that's 9, and I add 2? That's 11. What if I took this, multiplied it by 3, and added 2? That'd be 12 plus 2, 14. What if I took this position, multiplied it by 3, and added 2? This works. So if the position were just called n, what's the rule? Well, I would take the position, multiply it by 3, and then add 2. And that's exactly right. 3 times n plus 2. That's the general algebraic expression that captures this rule. This is an example, by the way, of an arithmetic sequence, because we're adding 3 each time, and this is the recipe. And let's just check it out, if you don't believe me. Let's look at when n equals 3. If n were 3, what would the term be? I plug in 3 for n, so I see 3 times 3, that's 9, plus 2 is 11. And that's exactly what we saw. 3, we get 11. So you can really see it happening in actual life. Absolutely cool. We can find a pattern, and then we can produce a general algebraic expression that captures the whole thing. Absolutely fantastic.